Hi, my name is Tim Miller. I'm one of the technical service contacts at Acrochem. In this technical solutions video, I will run through the process of developing a neutral rubber compound that can be used for colored, non-black applications. These discussion points will be general guidelines without a lot of detail for special situations. Acrochem offers its customers a color matching service. Just send us a couple of pounds of the neutral compound and we will match to your specific target. It's a lot easier for us to do this in-house because we have a wide palette of pigments available to complete the match properly. We can normally compound around special situations such as weather resistance or FDA applications. So let's begin by setting some ground rules. We realize that most rubber chemists are very interested in requiring that the technical properties of the finished compound will meet their specifications. Sometimes, from a compounding standpoint, formulations will need to be adjusted to provide for a more suitable neutral compound that can be pigmented more effectively. And on a relative cost basis, pigments are very expensive, so it's critical to start with raw materials that will provide the most suitable economic formulation. Our first formulating ingredient will be the polymer. This provides a good visual on how the polymer selection can greatly influence the final color. Polychloroprenes are very prone to darkening and turning more amber in shade upon vulcanization and exposure to sunlight. Moderate amounts of titanium dioxide are needed to compensate for this effect. In this diagram, an NBR PVC compound is compared to a polychloroprene compound. The formulations have similar loadings for polymer, filler, and plasticizer. Cure systems are adjusted to match what is needed for the polymer. 1 part of organic blue, in this case 626 Blue MB, was added to each formulation. Note how much cleaner the NBR PVC compound appears when compared to the polychloroprene compound. The chloroprene compound has a green undertone and will require significantly more titanium dioxide to compensate for the differences. Next, let's take a look at the fillers and extenders and the role they play in compound development. Fillers can provide opacity to the compound without any tinting value. An example of this is calcium carbonate. Calcium carbonate only opacifies the compound. It does not provide tinting value like titanium dioxide does. Other fillers, such as hard kaolin clays, are opaque and provide a tinting value. This may be in the form of a buff, beige undertone, all the way to exhibiting a very bright whitening effect. Other fillers may be translucent or nearly transparent. Good examples of these are silicas and silicates. Let's take a look at the following graphic. These photos show the same neutral rubber compound filled with 50 parts per 100 rubber each of hard kaolin clay, a high brightness water washed clay, in this case Polyfill HG90, and a white silicate Mansil ZX. The hard kaolin clay is significantly darker and less chromatic than the other two. The Polyfill HG90, while significantly better than the air-floated kaolin clay, still lacks the vibrant color that is exhibited in the silicate Mansil ZX. This chart illustrates the additional cost of using hard kaolin clay versus using the silicate. The cost doubles because of the additional titanium dioxide and colorant needed to compensate for the dark amber undertone of the inherent color of the hard clay. Our third component of the formula is the plasticizer or process oil. Most process oil suppliers will be able to indicate whether an oil has good UV stability. It is best to check with them for their recommendation. It's important to note that UV performance and process oil color change will affect the final color rendition of the compound. Our fourth and final component of the formula is the vulcanization system. In this graphic, we see the UV exposure performance of the non-black EPDM compound. This display provides a good visual of the differences between cure systems that use peroxide and those that require sulfur-cured systems. It also provides a good rendition when significant amounts of titanium dioxide are used. Note the initial discoloration as well as subsequent additional discoloration in the sulfur-cured system with UV exposure. As titanium dioxide is added, the color change improves upon UV exposure. The peroxide cure with just 2% titanium dioxide has about the same color stability as the 40% titanium dioxide in the sulfur-cured compound. Peroxides offer a much better initial color as well as better color stability when exposed to UV. However, if you prefer a sulfur-cured system, avoid accelerators and antioxidants that discolor. Your Acrochem technical service team can provide more help in this area. Thank you for watching this technical solutions video, and feel free to give us a call at Acrochem. We will be more than happy to provide insight into meeting your colorant and chemical needs. At Acrochem, the way we see it, your success is our success.